feel free to keep talking.
Okay, so the entire back of my neck, where the around your neck headphones touch, there are no headphones that I own that I can use anymore.
Yeah.
And this was just like a spontaneously, I started having some problems right before I went to Israel. So for those of you joining the conversation, I'm one of those unfortunate human beings that randomly out of nowhere developed a latex allergy. And so these earphones are currently like I can feel new hives starting behind my ears.
Can you, sorry to ask you this, can you somehow center your camera on yourself?
Yes. I mean,
Because right now you're sort of half cut off when. Perfect. And what's that over beside you? No, no, no. Stop it. Go back. There you go. It's okay if they're there. Yeah,
there's a green
that's
screen
fine.
in the chair
Yeah,
looking like a dead alien.
yeah, it's fine. What's
Okay.
the globe that's right beside
It's
you?
a moon.
Oh, can you bring it closer to the camera so we
Yes.
can see it? Oh, that is so cool.
Yeah, so this is one of the really cool ones that's produced at the Lunar and Planetary Institute. So it has all the names and it's based on Clementine data.
Mm-hmm.
The camera doesn't want to focus super close.
No,
There it
yeah, it
goes.
worked. There we go.
So
Oh, that's
yeah, it's
fantastic.
super detailed. It's all Clementine data and has all the names. And yes, these things are amazing. They also make them for, come on, camera, most most of the other worlds that have been well mapped.
I'm going to say hi to a bunch of people. Hello to Aiden Granfeld, Arnold Post, Astro B, Blair Pigeon, Bor Klankar, Brian Burke, Chris Adams, Chris Bamford, Frank Tippin, Gaida Saud, Gordon Dewis, Graham W., Harry M., Holly Meyer, John Seffield, Quad Libbet, Leonard Clark, Linda Sedick, Mark Frick, Mr. Tom Harbin, Nancy Graziano, Paranor 001, Rinstro, Rick Schwartz, Susie Murph, Timothy Kuiper, and Tijuan Tijutu, Tony Raggett, Umu, and Zappan. Hey, everybody. And I think somebody just said hello. So where are you?
I am at the headquarters of the Astronomical, I should look at the camera. I'm at the headquarters of the Astronomical Society of the Pacific in San Francisco. Tonight, I will be departing here and going up to see really good friends of the show, Phoenix and Rux, who happen to also be like my real world best friends. So you can actually see the ASP logo up
Mm-hmm.
behind me, and they have a little tiny, really well equipped baby studio. So it has the nice background,
Yeah.
more, and then they have like
Oh,
totally done the
oh,
walls.
that's great. And the door.
Yeah,
Yeah, no, I was thinking it actually
it's
sounds pretty good. It sounds very nicely muffled. It makes you want to just cover all the walls in your office with sound
quilts.
baffling, doesn't it?
Yeah,
Yeah.
I
I'm
have
tempted to
to
do that
work
here
in there.
actually and just start covering my walls with and maybe build a little wall beside me or something. I don't know. It's a little hollow sounding, so right on. Well, say hi to everybody at the Astronomical Society of the
I
Pacific.
will.
That's awesome. That's, I mean, they are such a great partner for everything that we've been working on. And although they forced you to get a big, long, very complicated title that I have to read out every time, I still, really appreciate their support and assistance. So say thanks and say hi.
Yes,
I can't wait to
I
visit them.
will. I will do that. I managed to open up the dictionary instead of opening up Audacity. I'm not, my computer lost its mind.
Don't do that. They are not the same thing. All right, so
Oh,
if you're
shoot.
wondering what
This
it is that you
computer
have
doesn't.
stumbled into, you're about to watch an episode of Astronomy Cast. We are going to record for, I don't know, however long I decide until we're done. And then we will stop and we'll stick around and we'll answer your questions about space and astronomy for the rest of the time. Again, until I've decided we've had enough. So people are saying you're a little overly lit, which I kind of agree. You're like sort of.
If I'm overly lit, you can't see that my face is covered in
Oh, I
hives.
see. All right.
This was strategic.
Oh, okay, okay. So we'll stick around, answer your questions, and or until the pain makes Pamela take her headphones off.
Oh, God.
Whatever comes first, we'll just go from there. One for the second half, you can always try taking off the headphones and then just run the
Yeah.
audio. I find Zoom isn't too bad. I haven't had a lot of echo, so let's just get it right for the audio recording.
Okay, so I'm going to auto record onto my Zoom just because it turns out this computer doesn't have Audacity on it. So I'm going to record directly onto
Okay,
this.
so mic control, put that thing somewhere nice in a close to your face as humanly possible. Don't touch it.
Yeah, touching it has always been a problem. Crap. There's a box.
Did
I'm
you
going to
run
grab
out
a
of
box.
books?
Yeah, I have my laptop on all the books in the room.
Yeah.
I'm going to grab a box. Hold
All
on.
right. So we waited.
And I'm actually going to take down my hair so that the headphones are touching my hair instead of
Nice.
my skin. Otherwise, I will begin to claw my ears off
Yeah.
halfway through the podcast.
Perfect.
Okay.
Nice. Good call. All right, let's do it.
Yeah.
All right. Let me get my intro. Here we go. You ready? Press record. Say hello to Chad.
Recording. Hi, Chad. How are you doing?
Astronomy Cast, episode 487, Dark Matter Update. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. I'm Fraser Cain, publisher of Universe Today. With me, as always, is Dr. Pamela Gay, the Director of Technology and Citizen Science at the Astronomical Society of the Pacific and the Director of CosmoQuest. And Pamela, you are actually at the Astronomical Society of the Pacific, which I think is awesome.
I am. I'm in San Francisco. As soon as I'm done with the workday, I'm heading up to Sacramento, and yeah, it's great to actually be like at the headquarters of the company I work for, and get to see some of my best friends, which I made strictly because of this show.
Right on. And a huge thank you to the Astronomical Society of the Pacific for their support of all of the kind of educational work that we do through CosmoQuest and Astrosphere. And, you know, we couldn't have a better partner in being able to get all this educational information out and be able to get all the citizen science done. They've been a real treat to work with. And I can't wait that I get a chance to come down and visit them. So one just big piece of news, which is, as I think I've mentioned briefly, Dave Dickinson and I are working on a book, the Universe Today Ultimate Guide to the Cosmos, I think. I forget the exact name. We're still working it out. But the gist is it is a sort of how to be an amateur astronomer and just like all of the sky charts and what to see in the night sky and how to pick a telescope and just that really comprehensive book. And we sent in, you know, Dave's been writing his heart out and delivered the manuscript last month, and then we just wrapped up all of the photographs. And that's the part that I'm most proud of, is that we've got, I think, 60 plus 70 astrophotographers who have contributed photographs to this book, and they're all going to be pictures that people have never seen before. They are, you know, amateur astrophotography of all of the planets and the sun and a lot of the deep sky objects and the Milky Way, and really great artistic work. And I'm just so proud and so thankful for all of the photographers who participated. And, you know, we'll give you more information as we actually get closer. But wow, what a load off to put this thing to the, you know, off to the publisher. So I said I'd never write another book, and I didn't because Dave did it, but it still was a tremendous amount of work, and I'm really, really proud of what's come together, and Dave's just done a great job. So stay tuned as we get closer to the actual book, and then maybe you'll have to interview us for Astronomy Cast or something. All right, let's move on. So, last week we gave you an update in particle physics. This week it's time to see what's new in the world of dark matter. Spoiler alert, we still have no idea what it is, but maybe a few more ideas for what it isn't.
This is true. Now, this is one of those great updates we get to do where we go from knowing definitively that dark matter is a thing and not a modification to gravity, uh, which we had, I think, in our first season. And now we can actually say with even more certainty that it is um, totally a thing with lots of more lines of evidence.
Right.
So, just in the time that we've been doing this show, we have gone from we don't know what dark matter is to dark matter is stuff to dark matter is definitely stuff. And here are three lines of evidence.
Right. And before we get into that, I think it's funny, now that we've been doing the show for 10 years, we're doing episode 487, we're closing in on episode 500, and people are always like, what are you going to do for episode 100? Are you going to look back at all the stuff that's changed? What are you going to do for episode, and what are you going to do for episode 500? I'm really glad it's almost like we're doing update season as opposed to necessarily we try to go through one episode. I think this was genius of you to put these episodes into the queue, and I wouldn't be surprised if this runs us through up to 500. But because we went after a lot of that low-hanging fruit when we first started the show. We're like extrasolar planets, dark matter, dark energy, black holes, right? All of this stuff that have just been puzzles that have plagued astronomers. I think dark matter was our third episode. Dark energy was our fourth, right?
Yeah.
So, we knew that these were gigantic mysteries, and we would have thought that there had been more, that there would have been, if you'd asked me 10 years down the road, will we know what dark matter is? I probably would have gone, yeah, probably. So here we are. You mentioned that we have like three lines of evidence, but can you just sort of set the stage for what we thought dark matter could be, and then how we got to the point now where we've been able to sort of knock off some of those possibilities?
So to give a really quick roundup of the history of dark matter. It was first discovered before you or I were born as some weird thing that was causing stuff in galaxies to orbit faster than it should. And that was deeply mysterious. And then we started looking at galaxy clusters, and it was seen that there was the exact same problem of stuff in galaxy clusters orbiting faster than it should. And the amount that things were orbiting too fast was a function of how far the stuff was from the center of the galaxy, from the center of the galaxy cluster. And so there seemed to be this diffusion of huge exclamation mark, question mark. We didn't know what. And it had different distributions in different galaxies and different distributions in different galaxy clusters. So it was theorized that either there is this stuff that we didn't know what was that existed in different proportions and densities in different environments, or there was something about gravity that required us to modify the equation for gravity at great distances. And pretty much canon for the professional astronomy community was it's a thing, and we shall call this thing dark matter because we don't know what it is. And like didn't know what it is at the level of didn't know if it was a distribution of black holes and cold dark white dwarfs and other high
Yes.
mass compact objects.
Neutrinos.
Yeah, we didn't know if neutrinos had mass or not. We didn't know how much mass they had because they refused to interact in a logical manner.
Yeah.
Um, so all we knew was dark matter was probably stuff that you can actually account for the dark matter in our galaxy by putting one Acme brick per solar system volume of space. And so it could be like rogue asteroids, it could have been anything. All we knew was there was stuff that was exerting a gravitational influence that was acting like on aggregate there was a bigger mass in the center of the galaxy.
I just want to note that you said stuff in a very Phil Plate kind of way. Like anyone, I don't know if anyone else caught that, but wow, that was the way Phil Plate would have said stuff. But anyway, um, so so this whole idea of MOND, this modified Newtonian
Yeah. Gravity.
dynamics,
Yeah,
gravity, yeah,
dynamics.
yeah, is out. But now we have these 3 lines of evidence which
Yes.
are really helping us at least nail down some of the characteristics of
Yes.
dark matter.
And one of the early shows that we did in which I screwed up throughout the entire show. Um, I kept saying it was the ballet cluster and it was actually the bullet
The
cluster.
bullet cluster. Oh no.
Yeah, and no
See,
one caught me until the episode was recorded and posted.
I see. So and this is the thing. I would have caught it now, but I
Yeah,
wouldn't have caught it then.
because it was brand new
Brand new.
research.
Yeah.
And what the research on the bullet cluster that I renamed in our past episode, what we learned was there were these two galaxy clusters in the process of colliding. And folks used gravitational microlensing to look at how various background objects had their shapes distorted. Because with galaxies, if you take a whole bunch of galaxies and image them, they should average out because of the random orientations of galaxies. They should average out to be perfect circles. But they were actually averaging out to be more like teardrops and other distorted shapes. And you can work backwards from the distorted shapes to figure out the gravitational distribution that is altering all of these shapes. And they mapped out with this technique where all of the dark matter was in this merging cluster. And what they found was, according to the distributions, the dark matter had pretty much just like passed through each other with no interactions, while the luminous matter, the stars, the illuminated gas, the normal stuff, had all gotten distorted and compressed as the luminous stuff collided and distorted the galaxies.
Right.
And this was the first hint that dark matter is stuff.
Mm-hmm.
Still don't know what it is,
Right.
but we could add the word non collisional stuff.
Right. And then and I even remember you brought up this term of this small cross section.
Yeah.
Right. And that was actually a term that I don't think I was familiar with, right? Just this idea that the particles won't bonk into each other as clouds of them come past each other.
Right. And we know that this is a thing that happens because of neutrinos. Neutrinos are like, I don't care. I'm going to keep going. I just don't
Yeah.
care. I
Light year
can't
of
be
lead, no
bothered.
problem.
Right. And it appears that dark matter has the same can't be bothered to collide mentality as neutrinos. And so when we look at colliding galaxies, colliding galaxy clusters, we can use this gravitational microlensing to figure out the distribution of dark matter. And another episode that we did was on the Cosmos Project, where they were able to map out the distribution of dark matter in a fairly large column of space. what they did was they looked at the distribution in distortions to galaxies at one epoch, at the next epoch, at the next epoch. And the furthest galaxies are going to have their light distorted by everything. The slightly nearer galaxies are only going to be distorted by the stuff between them and us. The nearest galaxies are also only done by the stuff between them and us. And because the distortions change with distance, you can use that changing distortion to map out the galaxy's dark matter in the intervening space.
Right.
So we have this amazing map now, not just from Cosmos, by multiple different projects that shows that galaxies are inside these vast halos of dark matter. And some of them have bigger halos, some of them have smaller halos. And sometimes we see dark matter that doesn't have any luminous
Right.
matter in the center.
And the opposite as well. I mean, just a couple of weeks ago, they announced that they found a galaxy that had no dark matter in it whatsoever. And the way they had determined this was by calculating the motions of the galaxy clusters moving through the galaxy. And they determined that their motions were only due to the matter that they could see alone. And so this was a galaxy that had no dark matter in it whatsoever. And as you said, there are galaxies that are just the opposite, that are essentially only dark matter. I love this idea about with dark matter that we don't know what it is, but we
Mm-hmm.
can use it as a telescope.
Yes. And what's super amazing about this galaxy without dark matter, its name is NGC 1052. It's what's called an ultra diffuse galaxy. This is a galaxy where the stars are so separate that you can look through the galaxy. And by measuring the rates that these stars are orbiting as a function of distance, because they can see these individual stars, they were able to figure out that all of these motions could be accounted for just from the luminous matter. This was the galaxy we expected to see back when Vera Rubin first started doing her work studying motions in galaxies and discovered dark matter. So here we are finding this like holy grail of astronomy, essentially the galaxy that acts like we originally predicted, which means it has no dark matter. And if you can have a galaxy that has no dark matter, and you can have a dark matter halo with no galaxy in the center, and you can find everything in between these 2 points, that makes it hands down, no questions asked, dark matter is stuff,
Right.
because it is stuff that can gather in large amounts, and it is stuff that can simply not show up. And if we actually required a modification to gravity, we would never have a galaxy that has no dark matter. Because there is always this lingering, is there like maybe a small term that's there that we just can't separate out, and we do still need to modify gravity? And the answer is no, we understand gravity. And that's
Yeah.
fabulous. There's no longer a question mark.
But that is not, I think, if you talk to a lot of cosmologists, that line of evidence, although compelling, is probably not the best one. That's not the smoking gun that says for absolute certain there is dark matter. But I think, and I'm assuming you're going to get to this in a second, right? The one is our old friend, the cosmic microwave background radiation, gives us the definitive there is absolutely dark matter.
The cosmic microwave background, actually what we see in it doesn't help tell us if gravity might not have an extra term. It tells us that there is definitely a substance or a extra term to gravity. So in order to say dark matter is stuff and not a failure of understanding of gravity, this is where that not having it actually is the yes, gravity is fine and dark matter is stuff. So cosmic microwave background is just one more, the universe has a larger density than we knew about. And it tells us that it's either a larger mass density or gravity doesn't behave the way we thought it did at large distances. We can't differentiate those two.
Right, but from what I understand, there's sort of oscillations in the CMB, and sort of,
Yes.
you know, if there was dark matter, they would have one which matches the observations, and if there wasn't, they would have a different representation that we don't see. And so it's like the model for a dark matter as a particle is well represented by what we see in the
Yes.
oscillations in the cosmic microwave background. So anyway, that's whenever
It
I have these conversations with cosmologists and they always want to sort of just remind me that the bullet cluster, for example, are great evidence, and these great maps are wonderful, but boy, is the evidence there in the cosmic microwave background.
and the unfortunate thing is, just like there are cosmologists who claim that through cosmology and particle physics you can prove the existence of God or you can prove the not existence of God. There are also cosmologists out there that are able to create equations for gravity, working in different ways in different conditions, and come up with a theory, a modified Newtonian dynamics theory that allows you to erase dark matter as a particle.
So, how many of your lines of evidence did you get through? Did you get through two?
Uh, so the fact that you have halos with no luminous matter inside of them,
Mm-hmm.
the fact that you have luminous with no dark matter, and the fact that you can use microlensing to trace out the distribution are the three lines of
Right.
evidence.
And I'm gonna throw the CMB in there as well. But okay, so let's talk a bit about then the search for dark matter. You know, we now assume that it's some kind of particle. It has a
Yeah.
cross section, although very small, so it doesn't, as I mentioned, use the scientific term, bonk into each other. What attempts have been made to try and figure out what it is, or at least what it isn't?
There's two major kinds of experiments that are being done. The first is you take a particle accelerator, whether it be Fermi National Labs, CERN, or any of the other colliders in the world, and you collide different things together and look what falls out, and you hope for some particle that has a high mass and other characteristics that make it not work and play well with the electromagnetic force. You hope for that to fall out of the collision so you can go, oh, I have found a particle that is not a neutrino that has all of the characteristics we need. Or you use the same kinds of detectors that we use to find neutrinos. These are large tanks built deep underground, usually in some sort of an old mine, and you fill them with highly reactive fluid. It's actually, for one kind of reaction, it's a heavy water experiment. In another kind, it's very much the kind of fluid that you actually use to dry clean clothes. And these different kinds of fluids are highly reactive. You add just the smallest snort of energy and they emit photons. And with this highly reactive fluid, you put it underground so you don't have to worry about just your random cosmic ray triggering a reaction. And the neutrinos, which really don't care what they're passing through, will, in small percentages, actually interact with these fluids. And different kinds of neutrinos interact in different situations. The hope is that dark matter will also, but at a much lower percentage than even neutrinos do, react with this kind of fluid. And so we'll see reactions that don't have the correct energy to be one of the three flavors of neutrinos and will have the same lack of interaction characteristics. And we'll say, here be dark matter.
Right. And so that same idea, like as you said, neutrinos don't have much of a cross section. They'll gladly pass through almost a light year of lead.
Yes.
And so if you generate or have a ton of neutrinos moving through this liquid, every now and then one is going to interact and you're going to get this cascade of particles, and it's going to allow you to detect it. So have any of these, because I know like there's one in Canada, there's at Sudbury, there's a great one in Japan that you always see those wonderful pictures of with the people in the boats with these crazy gold hemispheres.
Photomultiplier tubes.
Yeah, such a cool place. I'd love to be in that. And there are others. Has anything detected anything?
There have been some inconclusive detections. And by inconclusive, I mean they saw once this weird thing, but it had too little signal to noise to actually say, yes, we definitely found something. It's like the earliest detections of the Higgs boson. And the earliest detections of the Higgs boson, people were like, we think we see a signal. We think we see a signal at the correct energy. We're not entirely sure, but we're going to say we saw something at low signal to noise that is not a confirmation, but we want to make sure that we have a placeholder paper.
Right, for when the Nobel Prize comes later on.
And none of the placeholder papers got the Nobel Prize, but they wanted to like stomp all over their energy level and call it mine.
Yeah.
And so we're starting to see some of those early low sigma, maybe we saw something, maybe we didn't detections. Nothing definitive yet.
Now, when you mention that sort of low sigma, you're talking about the level of sigma, the level
compared to background noise
of certainty, right?
Yeah.
And so, when the Higgs boson was confirmed, and again, that was Nobel Prizes all around, they had detected it to a level of certainty that you could say for sure that particle exists there at that level of certainty. And I've even seen some recent potential discoveries of dark matter that had been that as more experiments had done, it was like, oh no, it was background noise.
Retracted.
Yeah.
And we saw a lot of retractions come out of early detections of what people thought were the supersymmetric particles at CERN.
Yeah.
So the issue is, have you ever been in a really dark room and closed your eyes and you still see this noise pattern?
Mm-hmm.
So that's actually in some cases caused by cosmic rays interacting with the retina in your eyeball.
Apparently, for astronauts, that's actually pretty distracting because they see them a lot more, and so they close their eyes and they just see a light show.
Yeah,
which
and
is kind of
super
scary.
Creepy.
Yeah.
Yeah. And the human brain, being what it is, will like start hallucinating things in this background noise. So that's the background noise of your eyeball. And you can imagine if you're in a completely dark room with your eyes shut and someone rapidly turns on and off a laser beam that is pointed at your eyelids, a low power one, you might think you saw something, but because it's a low power laser beam through your eyelids, you're not entirely sure because it might have just been a particularly bright cosmic ray hitting your retina. That's a low signal to noise detection. But at the same time, if your eyeballs are closed and your significant other or your friend or whatever comes into the room and turns on the lights, it's going to wake you up because you can totally detect that bright light through your eyeballs, and that's a high signal to noise detection.
Now, there's sort of two ways to go about it, right? In the case of, say, these dark matter detectors that we were talking about, this is you trying to essentially capture naturally forming dark matter particles that happen to be moving through the Earth. The other way is to generate them with something like the Large Hadron Collider.
Yeah.
How's that going?
Yeah, they have the exact same Well, it was actually the exact same discovery. They thought they had found some supersymmetric particles that would also account for dark matter, because that is one of the great hopes of a lot of these particle physicists, that all of these supersymmetric particles will actually be dark matter. And we're just not finding them. This
Right.
is what we talked about in the last episode, where we were like, the standard model seems to be totally good by itself. We don't seem to need underlying physics. Uh, it's just good.
Yeah.
So while Kepler's laws of planetary motion needed Newton's theory of gravity to explain the how behind the observable, with the standard model, we have no how and why. People came up with supersymmetric particles. They went looking for them, but CERN is only, as it stretches its energy to higher and higher levels of collisions, they're only really starting to hit the mainstream particle theories for
Right.
supersymmetric particles. So what they've ruled out is some of the lower energy, not
Right. Some of the
most
extreme
talked
ones.
about
Yeah.
theories.
I mean,
Yeah.
I love this idea, right? You've got some theorist and they've written a paper and they've said,
Yeah.
crank up the LHC to 11, and then you
Yeah.
should see, at that energy level, you should see this cascade of particles in all of your detectors, and that means you found dark matter. And then the folks at the
Yes.
LHC, they crank up the, the proton beams to 11, and they listen and they don't see that. And so then the poor theorist has to just take their theory and just go, well, that's in the garbage. And then,
And
who's
and
next?
what's hilarious is a lot of these theorists will say, no, 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 I actually meant 16. It's
Yeah.
the among observational astronomers, one of the things that I learned in grad school as a form of mocking theorists is, if you lock five theorists in a room, they will come out with nine mutually exclusive theories.
Right. All right. Well, I think I guess we need to come back in another 10 years, another 500 episodes, and we'll give you guys another update on how the search for dark matter is going. What's next week? You want to come back around to dark
Next
energy?
week is dark
Right
energy.
on. All right. That sounds
So we're
great.
just going to keep on
All
updating
right.
you.
We'll see you then, Pamela.
Bye bye. And now,
We save.
yep. Stop.
That's 487.
Yeah, but I just saved it on my Zoom, so I'll have to pull it off later. I love how the Zoom is so polite and is like, goodbye, see you.
Yeah. It's like a Japanese
This, by the
toilet.
way, is the reason I got detained in Amman.
Was your Zoom?
Yeah,
Really?
yeah.
Here's mine.
I need
I
to
this
switch
thing,
tabs.
if you have any interest in doing any like video work or anything, this thing is a Swiss Army knife. I can't recommend
Yeah,
Zooms highly enough. You can plug kind of any audio into it. They've got microphones on
yeah.
board. You can put the smaller microphones into them. They record really nice, high quality sound, and then you just pop out the little card and
But if you're traveling
yeah.
internationally, I highly recommend the H2. Uh, it isn't as high a quality, and you can't plug other mics into it. I don't think. I could be
Yeah.
wrong on that. But it without questions just passes through security. I've been stopped
Yeah.
in London and almost missed a connection. I was like in Amman, they were like, go sit on that bench, give us your passport, and we're going to have three large men watch you.
Wow.
It was, I think I got through security in Amman because they gave me permission to look up something on the internet on my cell phone. And I pulled up my Wikipedia page and I pointed at the microphone and I said, microphone, microphone, pointing at the Zoom. And then I pointed at me and I said, me. And after they looked at my Wikipedia page, they let me leave.
Oh, nice. Well, then
So,
it really sucks that my Wikipedia page has been kind of vandalized down to nothing.
So don't travel internationally with your Zoom unless you go to Japan
Yeah.
where it's made.
Right. Now I've traveled. The one that's given me the most grief was all the traveling I did with my blue snowball. Because
Really?
yeah, because it just kind of looks like a hand grenade or something. I don't know. Yeah. So
Okay.
I've had no end of problems. When I say no end of problems, like someone always wants to take it, look at it, know what it is. And I've had a couple of
Yeah.
people who are like, "Oh yeah, I've seen that before." Like you get the ones who've seen a lot of these and they know exactly what they are. But yeah, I've had the occasional one go like, "What is that ball filled with metal and electronics that kind of looks like a bomb?" So
Yeah.
yeah,
So apparently a stack of 5,000 stickers looks like dynamite. So I had one of my most embarrassing, not the most, but one of my most embarrassing security experiences at Washington Reagan Airport coming back with an entire like one of those little bags that you usually use to put your underwear in while traveling. I had it completely packed with lunar reconnaissance orbiter stickers.
yeah.
And this was 2 or 3 weeks after Trayvon Martin was shot and killed, and I was wearing a NASA hoodie because I was coming from a NASA event. So I'm branded NASA, and I only have a carry-on, and it has this compression bag of stickers. And they made me take my hoodie off, and I only had a tank top on underneath, stand there, and they took every item out of my suitcase one by one, shook it, and then sat it down. This includes all of my underwear, all of my underwear.
Oh.
So, yeah.
Hmm. Okay, let's get on with some questions.
Okay.
Ben Appleby wants to know if light takes millions of years to get from Andromeda to Earth, how do we know it's still there?
Because it would be really hard for it to go away.
Yeah.
So we're kind of assuming that, and this is actually a big philosophy debate. Philosophers will own you on this if you try and argue it with philosophers. One of the premises of science is what we see evolves along the understanding of the laws of physics. And so the fact that we currently see a giant galaxy right off our starboard, apparently, that is gravitationally bound to us and on a collision course, if we run our observables forward through time, we get to the Earth, not the Earth, the Milky Way and the Andromeda galaxy colliding in about 5 billion years. And since we don't see anything that is liable to like sideswipe Andromeda and tear it away from us, uh, we model it to say Andromeda is still there.
Yeah.
Now, a philosopher will argue with you that it could be completely gone, that nothing is deterministic and nothing is actually real. Those are conversations that cause me to swap my coffee for scotch.
Yeah. Now, I mean, like if you hear a car driving towards you and you close your eyes, you're not hearing the car at the exact distance that it really is. You're hearing the car after the sound took the time to get from the car to you. But
Yes.
if you hear that car getting louder and louder, and you know that it is, perhaps a millisecond off of where the car really is, it still does feel safe to assume that that car is still
Yeah.
headed for you and that, at any point the car hasn't disappeared.
Yeah.
So, as you said, right, like Andromeda's whatever, 2.5 million light years away. So, in other words, the light you're
Yeah.
seeing is 2.5 million years old, but it is going to take 5 billion years to get to us. So,
Yeah.
it's still on its way. You ever hear that thing where people say, like, oh, when you look up into the sky and you see all the stars, actually all those stars are dead, just like your dreams? It's not true. Those stars are all
But the
still
Eagle
there.
Nebula is shredded. So
Maybe. I've
so
actually heard now that it may be not.
it still has O stars in it.
Yeah, but those stars haven't necessarily exploded in the way and caused the damage that the people have thought. But the
Okay.
vast majority, like when you look up into the sky, the vast majority of the stars that you're seeing are large, bright stars that are at pretty actually at various distances, but they are the brightest stars in the sky. And it's, say, a few thousand light years at the most to some of these stars. They are not dead. They are all still there,
Yeah.
right? So your dreams, like those stars, are still alive.
Yeah.
All right. Brian Burke has a great question about planetary finding techniques, and I'm going to sort of give the quick version of it, which is, there's the transit method and there's the radial velocity method. The radial velocity is you detect the motions of stars moving back and forth. The transit method is you have to watch the stars going in front, and he wants to know how many exoplanetary systems are actually correctly aligned with those versions that we have. And I've got a treat for you, Brian, which is that you get a sneak peek of an upcoming video that I'm going to do as a QA show, and I got a special guest answerer, and I'm going to see if I can actually just play this for you. So let's see if we can pull this off. Give me 1 second. Okay, I love the timing. All right, hold on. Oh, maybe I can't do this. So, apologize in advance. See how big this is going to be. This could be a very large window. It's going to look super weird in a second here. Let's see what happens. All right.
That's a great question, Norman, but not...
Okay, so this was a question that was asked to Norman. Norman asked it, not you, and I apologize. All right, so this is Dr. David Kipping, who is a professor at Columbia University. Pamela, you may know him. You can't see his answer. I apologize in advance, but the audience will. Okay, here we go.
That's a great question, Norman, but not a straightforward one to answer. The percentage or fraction of planets which transit in front of their star equals the sum, the total, of all of the planet's individual transit probabilities. And that probability depends on two factors. So let's imagine that this disk is my star and this espresso pod is my planet. The chance that someone off to the side over there will see these two objects line up and thus cause a transit will be higher if I make this disk much, much bigger. So the transit probability depends on the size of the star, and that's different for every star system you look at. Now, hopefully you can also see that if I have my star and my planet very close together, maybe something like a hot Jupiter system, the range of angles which allow for a transit to be seen is pretty broad. Whereas if I separate them apart, maybe something more like Pluto around the sun, the range of angles is now much narrower, so the transit probability is less. So overall, the transit probability equals the star's radius divided by the separation to the planet. For the Earth-Sun system, that's something like 0.5%, whereas if I'm talking about a hot Jupiter, it could be as high as 10% or even higher than that. So the true fraction of planets which transit their star depends on the distribution of the planet properties, and that's something that astronomers like us here at Columbia University at the Cool Worlds Lab are trying to actively uncover.
There you go. David Kipping, he is with Columbia University, works in the Cool Worlds Lab. They have a great YouTube channel called Cool Worlds. Totally check it out. And it was a real treat. He's known in exoplanetary research as the exomoons guy. So he's the one who's done a lot of work in predicting and helping search for extrasolar planetary moons, which is sort of like some next level stuff. So
There's actually a third way that planets have been discovered, and this is how we've actually found exomoons, and this is through gravitational lensing.
yeah,
So you only get to detect the planet and moon once because it's a perfect alignment with a background star that with a foreground star
right.
that lenses the planet and the moon to magnify its brightness.
Yeah. Yeah. And in
Right.
fact, there's actually Wikipedia has a great list of all of the tried and true and even potential methods of finding planets. And now there's about 12 suggested different ways for finding planets.
Wow.
Even some more bizarre ones like eventually gravitation, you say gravitational lensing, maybe gravitational waves, who knows what could eventually be possible. The one that I'm most excited about is essentially the direct imaging of extrasolar planets, that you're going to have a really powerful telescope like James Webb, something like that, that's going to be able to detect these planetary systems at any angle just directly. You put a coronagraph in front of the star so that you can see fainter objects that are beside the star, and then you just take pictures and you detect planets. And that is going to be the technique, once that really gets figured out, that's going to go take everything to the next level, because then you get the other percent, right? The other 99% of the planets out there that aren't aligned with their star. I mean, it's such a shame when you think of how few of the worlds that are out there we can actually see.
Yeah. Anything else? And I have to admit, I'm starting to want to tear my ears off.
Well, why don't you switch to speakers?
Speaker. Yeah.
All right, and let's get another question. There was a dark matter question that I want to... Oh, wait. Can dark matter turn into stars? Yeah, David Kibbing would be a great guest for the Weekly Space Hangout. Can you hear me yet? Clearly not.
There we go. Now I can hear you.
Okay, great.
And I apologize for the fluffiness, everyone. My hair was up all day and I took it down just for the headphones.
Right, as a latex block.
Yeah.
So let's talk about can dark matter turn into stars?
No, because it's collisionless. You have to have things willing to collide and have fusion and nuclear reactions in order to get a star.
Can dark matter go into black holes?
Yes, but it's probably not a major constituent because, again, it doesn't like. So, like, if a dark matter particle is flying along and gets too close to a black hole, it's going to get trapped like everything else. But a bunch of dark matter, because it doesn't like to interact, is not going to form a black hole.
Right. And so you would need to have that direct hit. You'd have to hit the event horizon for it to go into the black hole. Anything else, it's probably going to then, it's going to miss. Unlike things like planets, which just have to get within the Roche limit, and then they get torn apart, and some of it's going into the black hole, and some of it isn't.
Yeah.
Mark Frick asks, so TESS launches April 16th. How long before TESS starts actually doing science?
So TESS has what is best described as the world's craziest orbital injection plan.
Yeah.
So it's going to take roughly 70 days, I think, to get where it's going. And then they have to go through, there's first an outgassing phase where you basically wait for all of the gases that were trapped in your spacecraft to escape.
Yeah.
And then you very slowly and carefully, while testing everything, turn it on. I honestly wouldn't be surprised if it was 3.5 to 4 months.
That's what I've heard as well. Yeah.
Yeah.
The orbit is super, super cool. It's this P2 lunar resonance orbit. You can tell both by my hair and my knowledge of the mission that somebody's just done an episode on this. So it's going to go around the Earth twice for every time that the moon goes around the Earth once.
Yeah.
So at its closest point, it's going to be like something like 30,000 kilometers altitude, and will transmit all of its data, and then it will fly out to about 250,000 kilometers altitude. And all this entire time, it's going to be doing all of the all of these observations. Yeah, it's going to look at 500,000 stars in our nearby area and just comprehensively find every single bright star that has planets going around it. It is
Well, and it's not
so
even
exciting.
bright stars because it's a uh, volume of space that is equal in all directions. So with Kepler, they're looking at the Kepler field. So they
Mhm.
have a specific field, and because it's a specific field, it's when that field comes really close, it's a small volume of space. And as they look out, the volume gets larger and larger. So Kepler is actually finding the majority of its planets at fairly high distances. With TESS, because they're moving the spacecraft around to go, there's a red dwarf, there's another red dwarf, this is a super bright star, but it's nearby.
Yes.
We are going to get what's called a volume limited sample that starts to allow us to get the statistical rates of, well, we know this is the ratio of little stars to big stars on average throughout a given volume of space. And now I know X percentage of red dwarfs always have
Mhm. Mhm.
this, and Y percent always have
Yeah.
of blue giants or whatever.
It's not going to be as sensitive on a star by star basis as Kepler
Right.
was, but it will be comprehensive in that it's going to be looking at the entire sky,
Yeah.
and it's going to be able to it's going to move from star to star 1 minute at a time. So it's going to do the entire
Yes.
sky in about 2 years, I believe. And
Yeah.
so it will find Earth 2.0. It is the one that's going to find it. The estimates are it's going to turn up 500 Earth and super Earth worlds over the course of its detection run, which
And it's going to be a race between it and Gaia on who finds Earth too, because Gaia has the capacity as well, but it has a different strategy. So it
yeah,
will luck into it, whereas Tess is systematically looking for it.
yeah.
Uh, but because Gaia's been up for a couple of years, it may happen to get there first.
The great thing about Tess is it's going to serve as the scout to find
Yes.
these worlds to then pass them back where people can do follow-up ground observations. Kepler found a lot of worlds that, I mean, I just
You
shared a thing
can't
on
follow up.
Twitter. The TRAPPIST-1 system is just a one blobby pixel square with another blobby pixel square beside it that's maybe a little bit darker, and that's as much
Yeah.
data as you get. While
Tess is looking nearby.
Tess is looking nearby, and it's going to just be like, it's going to be dumping all of these potential objects in front of astronomers, and then they can turn with gigantic telescopes and the Earth-based stuff and ground-based detections, and then really get to the bottom of what these worlds are like. So Tess is just going to open up the the just the amount of places that we know that have planets just beyond all comprehension. So, but you're exactly right. Gaia, this isn't even Gaia's job. And it's like, oh, and by the way, in fact, the new Gaia release is coming out, and I think they've got 1.6 billion stars in their next data release.
Yeah. It's kind of
Mind
amazing.
bending.
And it's once when and if James Webb actually starts working, uh, it has the capacity to measure the atmospheres of these planets that are around tiny stars quite easily. And so this is going to open up a whole new level of follow up.
Yeah.
We'll be able to see with other kinds of stars the atmospheres of planets as well. So this will be a multi-telescope follow-up, but James Webb is a definite part of its plan.
Yeah, for sure. And the trick is going to be that these Earth 2.0s, these Earth-sized worlds in the habitable zone of sun-like stars, take multiple years to confirm that they're there, right? The first time you see it go past, you're like, oh, there's a planet. Then you got to wait a year, like 365 Earth days, and like, oh, did another pass, and then you got to wait another year to really get that confirmation. So even when test begins, we're looking at 3 years plus for those first planetary candidates to start flowing in. And we could and should have had this thanks to Kepler, but then, somebody didn't give it enough reaction wheels. So, although I still love the way Kepler was able to continue using light pressure as the way to keep the telescope pointed perfectly. It is the best rescue of a spacecraft that I've ever heard of. So, but you're going to have to watch my video to learn more.
And I do need to get going, or I won't be allowed to get lunch.
I'm having so much fun. We hit 1 o'clock. I didn't even notice. All right. Well, thanks, Pamela. Thanks, as always, to everyone who is watching the show. Asked all your questions. We always appreciate it. If you want to join the chat, join the community, go to wshcrew.space, and they will hook you up. All right. Thanks, Pamela, and we'll see you. Are you going to be back home next week?
Yes, and I'm actually going to be home until mid-June. This is like the longest I've been home for a while.
Excellent. I look forward to hanging out next week. We'll see you then.
Yes.
Bye.
Bye-bye, everyone.